Hey guys, so in this video, we're going to learn about the second derivative. Now in order to understand this, we're going to start by looking at an example of a function. Let's say that I have the function f of x is equal to x cubed plus x squared minus 5x minus 2. And let's say that we have y is equal to f of x. And let's look at the graph for this function. So here we have the graph for the function. Here we have the curve that has the equation y is equal to x cubed plus x squared minus 5x minus 2. And what I want to do here is I want to find the coordinates of the turning points in this curve. In other words, I want to find the coordinates of the points A and B. And what we do know is that these turning points A and B are what we call stationary points. Again, stationary points are points at which the derivative is equal to 0. And we know that the turning point, the slope of the curve or the slope of the tangent to the curve is equal to 0. In other words, the derivative is equal to 0. So what we can do over here is we can find the derivative of the function f of x, that is f prime of x, and set it equal to 0. And we know the values of x for which it's equal to 0 will be the x coordinates of these turning points. So if we find f prime of x over here, the derivative of f of x is equal to 3x squared. That's what we're doing here. That's the derivative of x cubed. We're multiplying 3 and decreasing the power by 1. Plus 2x, we multiply the power again and decrease it by 1. So we have plus 2x. Then we have minus 5 over here, since the derivative of minus 5x is simply negative 5. And obviously the derivative of the constant term is equal to 0. And we know that at the turning points, the derivative is equal to 0. So if we set the derivative equal to 0, we get 3x squared plus 2x minus 5 is equal to 0. And we can solve this quadratic equation to find the values of x for which the derivative is equal to 0. So what we have here is we have the coefficient of x squared is 3 and we have negative 5 here. So 3 times 5 is 15. And since the negative 5 over here, we want to see what factors of 15 give us a difference of 2. And the factors of 15 that give us a difference of 2 would be 5 and 3. So we have 3x squared minus 3x plus 5x minus 5 is equal to 0. And if we factor out 3x, we have 3x times x minus 1 plus 5 times x minus 1 equal to 0. And we get 3x plus 5 times x minus 1 is equal to 0. And that gives us x is equal to 1, or x is equal to negative 5 over 3. So now we can clearly see that the x coordinate for the point A would be negative 5 over 3, since that's on the left-hand side of the y-axis. And the x coordinate for the point B would be x is equal to 1. And now we can find the y coordinates for these points by simply substituting the values of x into the expression that we have for the function f, since y is equal to f of x. For the point A, we know that the x coordinate is equal to negative 5 over 3. So the y coordinate will simply be f of negative 5 over 3. And when we calculate this, what we have to do is we have to substitute negative 5 over 3 for x over here. And if we calculate this, we get 121 divided by 27. That's the exact value for this y coordinate here. So we can say that the coordinates of the point A are negative 5 over 3 and 121 divided by 27. Similarly, if we wanted to find the coordinates of the point B, the x coordinate of B is 1, so we have x is equal to 1. So the y coordinates will simply be f of 1. And f of 1 over here is easier to calculate. We just have 1 plus 1 minus 5 minus 2, and that gives us negative 5. And therefore the coordinates of B, the coordinates of the point B over here are 1 comma negative 5. So we found the coordinates of the points A and B over here. So now let's talk about the second derivative. We can find the coordinates of the turning points by setting the derivative equal to 0, since they're stationary points. So the derivative would be equal to 0 when x is equal to negative 5 over 3 or when x is equal to 1. However, what we also notice here is that A and B are different types of turning points. A is what we call a maximum point, because points either side of A lie below A. So A can be said to be the top of a hill, and this type of a point is called a maximum point. On the other hand, B is what we call a minimum point, because points either side of B on the curve lie above B. So this is called a minimum point. So how do we differentiate between a maximum point and a minimum point? In other words, how do we show that A is indeed a maximum point and that B is indeed a minimum point? For that, we use the second derivative. Now the second derivative is the derivative of the derivative. In other words, we can find the second derivative by differentiating the derivative itself. And the notation that we use is f double prime of x. For the derivative or the first derivative, we use f prime of x. For the second derivative, it's f double prime of x. And similarly, since y is equal to f of x, For the first derivative, we use dy over dx is the notation to denote the first derivative, whereas over here it'll be d squared y over dx squared. So we can find the second derivative of a function f by differentiating that original function twice to get the second derivative. And the second derivative tells us the rate of change of the slope of a function, and therefore helps us determine the nature of the stationary point. In other words, it'll tell us whether the turning point is a maximum or a minimum. Now, how does the second derivative help us determine the nature of the stationary point? Let's look at tangents to the curve drawn at different points on the curve. Now, we know that the first derivative tells us the slope of the tangent itself. In other words, it tells us whether a function is increasing or decreasing at a given point. So if we start on the left-hand side of this point A, the function is increasing because the slope of the tangent, or the first derivative, will be positive. At the point A, the slope of the tangent will be equal to 0. The first derivative will be equal to 0. That's the stationary point. And then the slope will be negative, right, between the points A and B. For any value of x that lies between these 2 points, the slope of the tangent of the first derivative will be less than 0. The function will be decreasing. Again, the turning point B is a stationary point, so the first derivative is equal to 0. And then again, the function is increasing. So on the right-hand side of this point B, so that's what the first derivative tells us. It tells us the slope itself. It tells us what the value of the slope is and whether a function is increasing or decreasing. The second derivative, on the other hand, tells us the rate of change of slope. What that means is it tells us what's happening to the slope itself at a given point. So if you look at the point A, what we can say is that just before the point A, the slope is positive. At the point A, the slope is 0. And then just after the point A, the slope is negative. So what's happening to the slope around this point A is, as we're moving from left to right, we can see that the slope itself is decreasing. We go from positive to 0 to negative, so the slope is decreasing. So we can say that at this maximum point, the rate of change of the slope is negative. In other words, the second derivative is negative. So that means that if we have a maximum point, right, we know the maximum point is a stationary point, but at the maximum point, the rate of change of the slope is negative. In other words, around the maximum point, the slope is decreasing. There is a negative change in the slope. Hence, the second derivative is negative. So if the second derivative of a function is negative at a stationary point, then we can say that that stationary point is a maximum point. Similarly, if we look at the point B, what we can see is that the slope just before the point B is negative. At the point B, it's 0. And just after the point B, it's positive. So the rate of change of slope is positive. The slope is increasing around the point B as we move from left to right. So therefore, the second derivative would be a positive value at this point B. And if the second derivative is positive at a stationary point, we can say that it's a minimum point. That stationary point is a minimum point. So again, over here, we can first determine whether a point is a stationary point by evaluating the derivative. If the derivative at that point is equal to 0, we know that that point is a stationary point. Or if we want to find the coordinates of a stationary point, we can set the derivative equal to 0 and find the coordinates of the stationary point. If we want to determine the nature of the stationary point, we can evaluate the second derivative at that point. If the second derivative is negative, that means it's a maximum point, such as the point A over here. And if the second derivative is positive, it's greater than 0 at that point, then we can say that that stationary point is a minimum point. So now let's show that A is indeed a maximum point and that B is a minimum point. We can start by finding the second derivative. The second derivative over here is the derivative of the derivative. So if we take the derivative of f prime of x over here, the derivative of 3x squared is simply 2 times 3x. That would be 6x, since again we multiply the power and decrease the power by 1. And then we have 6x plus 2. That's the derivative of plus 2x over here. And the derivative of the constant term is 0. So we have the second derivative over here. Now we want to show that A is a maximum point and that B is a minimum point. So let's evaluate the second derivative at the point A. So we know the x coordinate of A is negative 5 over 3. So we're going to evaluate the second derivative at negative 5 over 3. And what we get over here is we get 6 times negative 5 over 3 plus 2. And what we have over here is 2 times negative 5 plus 2, so that is negative 8. So here we can see that the second derivative is negative. If the second derivative is negative at the point A, that means that stationary point is a maximum point. So therefore, we can say that A is a maximum point. Or we can say that A is a maximum. On the other hand, if we evaluate the second derivative at the point B, that going to be f double prime of 1. We're going to evaluate it when x is equal to 1, since that's the x coordinate of b. And 6x plus 2 is simply 6 times 1 plus 2 at the point b. So that would be positive 8. And since the second derivative is positive at this stationary point, we can say that this stationary point is a minimum point. So this implies over here that b is a minimum point. So that's how we use the second derivative.